I was gonna say I could have got 100% if I had just taken while I was walking that way. But I was
Okay. Anyone has any questions? Have taken quizzes that I haven't back before. There might not be anything for you. So I just handed out old quizzes that were handed back before, but some people never took them. So if you have, just look through the papers that I gave. If you find your quiz, keep it. Otherwise, you probably have all the quizzes back. Okay, so today what we want to do is try to finish chapter 10. You probably can't finish it, but we are going to finish it almost. So chapter 10, right before I came to the class, I sent you an email, and in the email I gave you the homework from section 10.3 and 10.4. I think yesterday when I gave you the homework, I probably made a mistake, because I think I said I'm giving you homework from 10 point. Did I say 10.4 or 10.3? Yeah, I probably gave you homework from 10.4, but then I said it's from 10.3. Probably. So today I sent you an email. I made it clear what problems are assigned from 10.3 and what are assigned from 10.4. Okay. So on Monday I will go over a few more exercises, and if you have any questions from the homework, I can answer those too. So today what we want to do is today we are going to continue with section 10.4, and the topic here is, I'm going to call this polar region, and it's not a standard term, but I'm going to use that. So what do I mean by polar region? Let's make a sketch here. What happened to oops. Okay, so let's make a sketch of the kind of region that I'm talking about. So let's say I have my horizontal axis here. Okay, and let's say this is the origin here, and let's say I have a angle alpha, which is given by this. So let's say this angle here is alpha, and let's say I have another array which is given by this array, and let's say the angle from here to here, that's beta. And let's say I have a curve, and the curve looks like this. So look at the curve between these 2 points. Let's say this curve is the graph of the function r is f of theta. R is f of theta. So if I look at the function r is f of theta in polar coordinates, the graph of that is given by this curve. The question is, let's say I want to know what is the area of this region. Okay, and so let's say A is the area of this region, and I want to know what is that area. So what we are going to show today is that this area is given by an integral, and the integral is from alpha to beta, okay, of half of f of theta, squared d theta. So if I have a region like this, now think of the region in the following way. The polar axis, as the polar axis moves from angle alpha to angle beta, as the polar axis moves from angle alpha to angle beta, it is sweeping through the region, okay? It is sweeping out a region bounded by this green curve, and that's the region that we are talking about. And the area of that region is given by this integral formula here. Now the question though is how do I know? First of all, that should be the integral. So in order to understand that, what I want to do first is the following. Let's say I have. We need to recall something from some facts about circles. So let's say I have a circle. Let's say I have a circle here, and let's say the circle has radius. Let's say the center of the circle is right here, and let's say the radius of the circle is let's say r I star. Why am I calling it r I star? Doesn't matter at this point. I'm just denoting the radius by that, but I'm using it because I'm going to use that notation later. So r I star is the radius, and let's say I have a sector of the circle, and the sector here is subtended by the angle delta theta. So delta theta is the central angle here, and I am looking at the slice or the sector of the circle subtended by this angle delta theta. Everybody is okay? So delta theta represents that central angle. Everybody is clear on that? My question to you, what's the area of this sector? What is the area of this sector? The area of area of the sector of the circle of radius Ri star subtended by the central angle delta theta. Okay, so what is this area? Anyone? Can anyone tell me what is that area of the sector? Well, if delta theta is 2 pi, what is the area? If delta theta is 2 pi, what's the area? Was that? Yeah, if delta theta is 2 pi, then you're getting the entire circle, right? So what's the area of the entire circle? Pi times the radius squared, right? So that's the area if delta theta is 2 pi. But it's not 2 pi, it's delta theta. If the central angle is not 2 pi, it's delta theta, then what should be the area? Well, I divide it by 2 pi and multiply by delta theta, right? By the ratio of the central angles. And so if I do that, what do I get? I get half, pi cancels out, Ri star, that's the radius squared, multiplied with delta theta. So that's the area of a sector of the circle of radius Ri star subtended by an angle delta theta. If the central angle is delta theta, then the area of the sector is given by half of radius squared times the length delta theta. Now here I'm assuming that we are using radian measure, okay? Just always take measure of angles to the radians. Everybody's okay with that? For this formula to work, theta has to be in radians. Okay. Any questions on this fact? Everybody's okay. Now let's go back to our question. Is I have this polar region and I want to show that the area of this region should be given by that integral formula. Okay, so why is that the case? So the first thing that I'm going to do is notice that for this polar region, theta, the theta values go from alpha to beta, right? For that region, theta values go from alpha to beta. So I am going to think of that as an interval from alpha to beta. So here is alpha and here is beta. And I am going to divide this interval into smaller sub-intervals. That is, I'm going to pick a partition of this interval. So alpha would be theta 0. And then I'll have theta 1 here. And then theta 2 here. Theta 3 here. ... At some point, I am going to have theta I minus 1. And I'll have... Is that mine? It's something else. I thought it was my laptop's noise or something. Okay, theta I, and then this is theta n minus 1, and beta would be theta n. So how many subintervals do I have here? Anyone knows? How many? N of them. N. There are n subintervals. This is my ith subinterval. Between theta I minus 1 and theta I, that's the ith subinterval. Now, so what I'm going to do is, in each subinterval, I am going to pick one number. So here I'm going to pick theta 1 star, Here I'm going to pick theta 2 star. And here I'm going to pick theta I star. Here I'm going to pick theta n star. So in each subinterval you pick a point. These are called sample points. Now let's look at the polar region again. Let me make another polar region here. So here's say it again. Oh yeah. Go ahead. Let me know when you're done writing it down. If you have questions, just raise your hand, and I'll try to explain again. Okay, so let's draw the polar region again. So let's say my polar region. Whoa. Okay, and let's say alpha will be drawn like this. Beta, I will draw it like this. And my curve, let's say, how did I draw it before? Okay. So, close enough, I guess. So let's say that's the polar region that I have, and in order to let's see how we should be approximating the area. So what I'm going to do, remember this is alpha, this angle here is alpha, and alpha is theta 0, and this angle here is beta, and beta would be theta n. Okay. What did I do? Oh, untitled page. That's the problem with tablets. Okay, so here's what we are going to do. We are going to, remember I picked theta 0, theta 1, theta 2. Each value of theta 1, theta 2, theta 3 will correspond to a point on the curve, right? You realize that? Because what is this curve? This curve is R is what? F of theta, right? So for each value of theta that we picked in the partition will give me a point on the curve. So let's say, what are those points? Let's say I have one point right here. Okay, so let's say this point here, that corresponds to the point R1 comma theta 1. So this is the point I get for theta 1. This point here that I have, I get it for R0 theta 0. Okay. Remember theta 0 was alpha, and I can pick another one. Let's say this point here is R2 theta 2, right? You see the point? And I'm going to keep doing that. And for the ith, remember when we took the partition of alpha beta, at some point I had the ith subinterval, right? So what's happening is that the first subinterval between theta 0 and theta 1 is giving me the first segment here. So this segment that I have here, right, that segment corresponds to the first subinterval. You see that? The first subinterval between theta 0 and theta 1, it corresponds to the region that I highlighted, okay? The second segment that I drew, it corresponds to the second subinterval. So if I keep doing that, at some point I will get the ith subinterval. So let me draw the ith subinterval here. So the ith subinterval will give me this segment, let's say. So this point here will correspond to theta equals to theta I minus 1. So this point would be Ri minus 1, theta I minus 1. Here I have dot 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 because I have all the other subintervals. And this point here, let's say, is Ri comma theta I. Right? So this segment, the segment in red corresponds to the ith subinterval, right? And of course, then I have dot dot dot, and the last one would be the nth subinterval will correspond to, let's say, this segment here. So this point here would be Rn minus 1, theta n minus 1, and this point here would be Rn theta n. Remember, theta n is the same as beta, okay? Theta n is the same as beta, theta 0 is the same as alpha. Is that making sense? So I divided the polar region into smaller regions, right? Okay, and I want to approximate the area of each segment by the area of a sector of a circle. Because each segment looks like a sector of a circle, right? Each segment here looks like the sector of a circle. So I am going to approximate the area of each segment by the area of a sector of a circle. Now, what circle of what radius, right? So let's concentrate on the ith subinterval. In the ith subinterval, remember I picked theta I star. That theta I star will correspond to, let's say, where is drawing? The theta I star will correspond to, let's say, this point here. So this point here corresponds to theta I star. So that means, let's say this point has coordinates Ri star, comma theta I star. Everybody's okay with that? The theta I star is between theta I minus 1 and theta I in the ith subinterval. So that, let's say the point corresponding to that is Ri star and theta I star. I am going to approximate this ith segment. I am going to approximate it by the area of a sector of radius Ri star subtended by the angle, I forgot to say, let's say the length of each subinterval here is delta theta, right? The length of each subinterval, let's say, is delta theta. So then, what's the central angle for the ith segment? For the ith segment, what's the central angle? What's the central angle for the ith segment? What is this angle? What's that? Delta theta, because I divided, what I said, I divided into subintervals having the same length, delta theta. So we are going to approximate this. We are going to approximate this by a circle, let's say. So this segment that I have here in red, so I am approximating the area of this segment by the area. Okay, so let me write it down. The area of the ith segment, and we are approximating that by the area of a sector of the circle of radius Ri star subtended by delta theta. You guys understand what I'm saying here? The ith segment, I'm saying let's approximate the area of that by using the area of a sector of a circle of radius Ri star subtended by the angle delta theta. And what is that area? We computed that area, right? Remember this fact? The area of a sector of radius Ri star subtended by delta theta is what? That's equal to half Ri star squared times delta theta, right? You guys are okay with that? Now remember, what is Ri star? Can someone tell me what is Ri star? R is f of theta, right? R is f of theta, so Ri star is what? Ri star is f of theta I star. So I am squaring that multiplied by delta theta. So this is just for the ith segment, right? But I should be adding my approximations for all the segments, right? So if I add them up, so I have to be adding I going from 1 through n, half of f of theta I star squared delta theta. So I am adding my approximations for all the segments. And is it clear that the more segments I have, the better approximation I have? So allow n to go to infinity. So n is the number of segments I have, right? So the limit as n goes to infinity, that should be the area, okay? That should be my area as n goes to infinity. The area of the polar region should be given by the limit. However, that limit is what? That limit is the Riemann sum, right? But it's Riemann sum of what function? That limit is the Riemann sum of what function? Well, this should be the integral from alpha to beta, and because it's the Riemann sum of the function what? Half f of theta, right? If I have this function, the Riemann sum of that function is exactly that sum. So I integrate with respect to d theta. With respect to theta, sorry. So that's how I know that the area is given by the integral. Everybody is okay with that? So what you need to memorize or remember is that usually what people would write here is that to remember this, you are integrating half of f of theta is basically r, right? So you are integrating a radius squared, right? Remember, r is f of theta, so you're integrating half of r squared with respect to theta. And so that's what you need to remember. So let's say I have the following question then. And your homework has several questions like this. Let's say find the area bounded, let me say, find the area of the region bounded by bounded by r is 1 plus sine theta. I want to remember what was the graph of this equation yesterday? We looked at the graph of this equation, right? What was the graph of this equation? It's a cardioid, right? It's a cardioid. So what we want to find is what's the area inside that cardioid. Okay? Now, can someone tell me what is the answer? If I have that the area inside the cardioid is A, what is that area? What's that area? What's the area of that cardioid? Can I think of that as a polar region? That polar region that you have, it is, remember how I said you should view this polar region? As theta goes from alpha to beta, the polar axis is sweeping through this region, right? Now, in the case of the cardioid, the polar axis is sweeping through the region inside the cardioid as theta goes from what to what? 0 to 2 pi, right? As you go from 0 to 2 pi, you are sweeping through the entire region inside the cardioid, right? Only once, right? Only once. So the area is given by 0 to 2 pi, half of r squared d theta, and in this case we have that r is 1 plus sine theta squared. And that's it. That's the integral that gives you the area. Yes? Yes, I do need the 1/2 still. Where did my half go, right? Have you guys watched the movie? There was a movie, it's called Where Did My Car Go, or something like this. Yeah, something like this. Now, here's something, and I'm not lying about. Here's the story, I'm not lying at all. I'm in grad school, and this is, usually I don't drive to campus, so I usually walk to campus to my office when I was in grad school. But sometimes I would drive. So this was one day, I think probably it was this Friday evening. So I drove. There was after Friday, the parking lots are free. So I went there. There was a garage. I parked it there. No, it wasn't a weekend, sorry. It probably was Thursday or something, and after 5, the garage was free. And I went there. I parked my car. I went to my office. I was working. And for some reason, I was at the end of the work day, I was probably happy. So I came back home, okay? So I came back home, and I just went to sleep. I woke up early in the morning because I had to go and teach a 8 a.m. section. And so I went out of my apartment complex. I was looking for my car, and it wasn't there. And for like 15 minutes, I was very, very confused. And I was about to call the cop, what happened to my car. And then after some time, I realized that I probably left it at the garage. So then I ran to the garage and found out that my car was still there. But I had a ticket by that time. So, all right. So, you can forget pretty easily. Car is not that big of a object, right? All right. So here's okay, so area is this. Everybody is okay? Everybody is okay with that? All right, so here's how you compute this. 0 to 2 pi. I'm going to take the half outside of the integral because it's just a constant factor. And what should I do? For the 1 plus sine theta squared, substitute with r? No. What you need to do, what you need to do is you have to expand 1 plus sine theta squared. Okay, so here's what you get. 1 plus 2 sine theta plus sine squared theta. Is that it? If I expand it, is that all I get? Okay, so now I can integrate term by term. So notice that first of all I'm going to get half 0 to 2 pi of 1 d theta. Second term, I have a 2 there, right? So that 2.5 will count. Why is it happening to me all the time? Okay, so this is 0 to 2 pi. You see that 2.5 cancels out. I have sine theta d theta plus half integral from 0 to 2 pi sine squared theta d theta. Now, well, the first one is pretty easy, right? It will be half times integral of 1 is theta, right? So you'll be evaluating theta at 2 pi and 0 and you'll be subtracting. So wouldn't you get just 2 pi at the end? And then for the second integral, the antiderivative is what? The antiderivative for the second one? Negative, in fact, negative cosine theta, negative cosine theta, which is 2 pi and 0. But you do know that it's got to be 0, right? You realize that? This integral? You realize that this integral would be 0? Why is that? Remember, the sine curve is like this, right? So there is a area above x-axis, area below x-axis. They cancel out, right? Remember, the integral gives you net area, right? So they cancel out. It's got to be 0. And then the last one is I have to apply a trick, right? And what is that? Sine squared of theta is what? That's the same as what you did in the quiz, right? In one of the quizzes. Sine squared of theta, it's half of 1 minus cosine 2 theta. Okay, so this is d theta then. And 0 to 2 pi. So I get pi here, the second term vanishes. And the third term, I get a quarter integral from 0 to 2 pi 1 minus cosine 2 theta, and what am I getting there? It's theta minus what? What's the antiderivative of cosine 2 theta? Was that? Half times sine 2 theta, right? So you get 2 pi and 0, and we get pi 1/4. Okay, if you plug in 2 pi, what do you get? You're going to get a 2 pi for theta. When you plug in 2 pi for theta for sine of that, it's 0, right? So that's all you get. And when you plug in 0, you get 0, right? So that's all I have. So then what do I have there? It's half pi, pi plus half pi, right? Am I getting 3 pi over 2 at the end? Everybody's okay? Questions at all on this? Everybody's doing okay with this? All right, so I am going to finish early. Okay, so this is it. Please look at the homework. If you have questions, let me know. Your next quiz on Friday will be over 10.3 and 10.4. Next week, Friday, the quiz will be 10.3, 10.4.